Hello everyone, welcome to my channel. In this video, you will learn the essential steps on how to design the one-way solid slab, including the following key points on how to determine loads and the maximum factor design moments of the slab. And we also cover how to establish the required slab thickness as per the ACI code requirements, and design the slab for tension reinforcement. Then we will verify the shear capacity, whether the strength of concrete is sufficiently enough to carry the shear. Then number 5 is temperature and shrinkage reinforcement and detail of rebars. So let's get started with our problem. The problem is design a reinforced concrete solid slab to support an 8-inch thick wall with a height of 8 feet across at the center of the slab, as shown in the figure below. Assuming the floor live load of 50 psf, given parameters Fy is equal to 60 ksi, Fc prime is equal to 3 ksi, and the unit weight of concrete is 150 psf. So this is the partial floor plan of our slab. So we have here the solid slab that we are going to design, and there is a crossing blockworks in here. So instead of providing beam to support the blockworks, so I'll just check the slab to consider to carry the blockworks. So by putting the blockworks at the middle of the span in order to create maximum bending moment. So PO is that is for the blockworks. So let's get started with our problem. We have given finishes 38 psf, and we have the ceiling plus the AC is equal to 20 psf. Lightweight partitions is equal to 20 psf, and the floor live load of 50 psf, and we have the Fc prime 3 ksi. Fy is equal to 60 ksi, and let's get started with our step-by-step solution. By the way guys, this is one of the previous projects, so I just formulate this problem, and this is our standard loading for this project. So first of all, we need to check the slab whether it qualifies with the one-way or two-way load distribution. So for the length to width ratio, we have 30 divided by 10, because we have 30 length of the slab and the width is 10. So that is equal to 3, which is greater than 2. So it is a one-way slab. Actually, this is according to the ACI 318 reference 8.3.1.2. That is one of the requirements for a solid one-way slab. So for the load distribution determination, estimate slab thickness as per the ACI code. So in the ACI requirements, we have table 7.3.1. So for the simply supported slab, we have a simply supported slab, 10 feet length, and that is equal to the L over 20. That is for simply supported slab. So with the length of 10 feet over times 12 over 20, and we are required to use the minimum of 6 inches. So T is equal to 6 inches. So if you use the lower thickness, let's say 5 inches, you are obligated to check the deflections, to check the deflection of the slab, and maybe you need to consider the crack sections, but it requires a longer time to calculate. So let's say we will consider the 1 foot width of slab. So finishes, that is consists of tiles and screed is equal to 38 PSF times 1 foot width of the slab, that is equal to 38 PLF, pounds per linear foot. Then the additional load, that is the ceiling plus the light partitioning, which is 20 plus 20, that is equal to 40 PSF. So the slab is, we used 6 inches divided by 12 times 150 PCF, that is equal to 75 PLF. So now let's continue to determine the uniform dead load, that is equal to 38, that is the finishes, plus the additional load of 40 plus the 75 thickness of the slab, and that is equal to 153 PLF. That is the uniform distributed dead load. So for the load P, which is due to blockworks, that is 79 PSF, this is the unit weight of the blockworks, 8 inches thick, times the height of 8 feet, that is equal to 632 pounds. So the uniform live load is equal to 50 PSF, and that is equal to 50 PLF. Now the factored uniform distributed load and the concentrated load, which is this one. So that is 1.2 times 153, which is the uniform distributed dead load, plus 1.6 times 50, which is the live load, that is equal to 263.6 PLF. That's the uniformly distributed load, factored uniform load. Then the factored concentrated load due to blockwork, that is 1.2 times 632 pounds, equal to 758.4 pounds. This is the one here. So the maximum factor design moment consists of uniformly distributed load and the concentrated load, that is the moment is equal to WL squared over 8 plus PL over 4, and that is equal to 263.6 times 10 squared over 8 plus 758.4 times 10 over 4. So the total moment is equal to 5191 pounds feet. Now we will determine the design, the tension steel reinforcement based on that maximum moment. So first we need to determine the steel ratio using the formula below. Assume tension control so that Fs is equal to Fy and Phi is equal to 0.9. So first we need to estimate the effective depth of the slab, that is D is equal to 6 inches minus 0.75 inches, that is the clear cover of the slab, minus half the diameter of the reinforcement, assuming that the rebars that we're gonna use is 0.5 diameter, which is number 4. That is equal to 5 inches, that is the effective depth of the slab. So using this formula, that is based on our standard formula for flexure formula, and if we substitute this to that formula, we will come up the quadratic equation. So to calculate the steel ratio, you need to determine first the value of M and the Rn. So that's why we are calculating the value of M here, that is Fy over 0.85 Fc prime is equal to 60 KSI over 0.85 times 3 KSI, that is equal to 23.53. And for Rm, that is equal to Mu over Pbd squared, that is equal to 5191, which is this one, our moment, times 12 over 0.9 times the unit width of 12 inches times the effective depth squared is equal to 230.71. So the still ratio, after we substitute all this value here to this equation, so you will have this 1 minus 2 times m times Rn over Fy. Then you have to do square root of this part here. Then you will get the value of still ratio of 0.00404. So guys, if you enjoy this video, please don't forget to like and consider subscribing if you are new to this channel. So let's go back to our problem. So check the for minimum still ratio requirements, that is based on the ACI section 9.6.1.2. So we have here the provision for minimum reinforcement 200 over Fy, and that is 200 over 60,000 psi. That is equal to 0.0033, which is less than to our actual still ratio. So then there's another provision that is 3 times the square root of Fc prime over Fy. So that is 3 times to the square root of the strength of concrete, which is 3,000 psi over 60,000 psi. That is equal to 0.00273. So normally this is the governing one. So now the still ratio ES is equal to rho BD. So our rho is 0.00404 times 12 times 5. So we have 0.242 square inch. So that is the required still reinforcement. So if we use number 3 bars with an area of 0.11, the spacing is equal to 12 over 0.242 over 0.11. That would give us a spacing of 5.44 inches. So let's say we will use number 3 at 5 inches on centers. So that is greater than, the actual area is greater than the required. So we are okay with this spacing. So now the next one is the temperature and shrinkage reinforcement. So we need to consider this in our slab design, because this will control the crack width requirements also. So based on this table from the ACI, I extracted this one, and that is table 24.4.3.2. We have the minimum still ratio here for shrinkage and temperature reinforcement. So we are using the deformed bars, which is 60,000 psi over Fy. So our still ratio is 0.00118. So if you are using the still ratio less than 60,000 psi, you need to use this one. So also there is requirements for the spacing. The spacing of the deformed shrinkage and temperature reinforcement shall not exceed the lesser of 5 inches and 18 inches. So here, the minimum still ratio rho is equal to 0.0018. That is for the deformed bars, grade 60 rebars. So ES is equal to 0.0018 times the gross area. That is 12 times 6 inches, which is equal to 0.13 square inch. So that is the required area for shrinkage and temperature reinforcement. Now if we use number 3 bars with an area of 0.11 square inch, so we are required to use the spacing of 12 over 0.13 divided by 0.11, that is equal to 10.15 inch. So number 3 at 10 inches on centers, that is top bars. No, that is not top bars. That is perpendicular to main bars. So our main bars actually is bottom bars. This is supposed to be bottom bars, and that is perpendicular to the main bars. Now we will check the spacing. So the provided spacing is equal to 10 inches on centers, which is less than to 5/8, which is 5 times 6 is equal to 30, or 18 inches. So our spacing of 10 inches on center is okay. Now we will check for shear. So for slab without shear reinforcement must rely on concrete shear strength, BC. So for BC is equal to 268.6 pounds per foot. So we have this one here. So we'll just multiply that by 10, divide by 2, and that is the reaction at the support. Plus 758.4, that is the point load, divide by 2. So the total reaction at the support is equal to 1,697.2 pounds. So that is the shear. So shear reinforcement are not required for the condition if BU is less than half of PBC. That is according to the ACI code 9.6.31. So PBC is equal to P2 times lambda square root of FC primes BD. Lambda here is equal to 1. That is if we are using the normal weight concrete. So PBC is equal to 0.75. That is the value of phi here for shear. Times 2 times 1 times to the square root of 3000 psi times the width of 12 inches times D 5 is equal to 4,929.5 pounds. So half of this, and that is equal to half of this value, that is equal to 2,464.8 pounds, which is greater than the actual required shear, 1,697 pounds. So meaning the shear reinforcement are not required. So if just in case the value of half of PVC is less than to the required shear, meaning you need to increase the slab thickness. You need to adjust the slab thickness. So here we have the section of the solid slab, our one-way solid slab. We have beam, and this beam is supporting the hollow core slab in the adjacent side as well as the other side also. The same thing. So this is the main reinforcement, which is number 3 at 5 inches on centers. And we have number 3 at 10 inches on centers. This is the shrinkage and temperature reinforcement, which is perpendicular to the main bars. So that's the end of our video, guys, and don't forget to like and subscribe. Thank you for watching. See you next time. Bye bye.